So let's move on to carbon's last bonding pattern, acetylene, C2H2. I've again removed 2 more hydrogens from that carbon. I went from C2H6 in ethane to C2H4 in ethylene and C2H2 in acetylene. So carbons have to be triple bonded in order for this to be the case. Since I only have 1 CH bond, I have to have 3 bonds between the carbons in order for that to work. So this is a triple bond. The triple bond will first contain 1 sigma bond from the hybrid orbitals. Every kind of bond, whether it's single, double, or triple, will start with a sigma bond. Then, beyond that 1 sigma bond, we'll have to have 2 pi bonds this time. So let's start by thinking about carbon originally. And here, this time I'll just make the electrons spread out. We'll just assume that it's like that. To do sp hybridization, I'm going to take the S and just one of the P's. So those will combine together, and I'll be left with 2 of these P's that are unhybridized, meaning they're unchanged from their original structure. So each of those will have 1 electron. So take a look at the structure. In green here, these are 2 sp hybrids. So to have sp hybrids, there are 2 of them, so they'll spread themselves out sort of 180 degrees from each other. Okay. That'll be key for us to show a 180 degree bond angle. What about these 2 unhybridized p orbitals? Well, I've got these 2 sp hybrids on one of the 3 coordinate axes. One of the p orbitals will be on another axis, the other p orbital will be on the other axis. So having an sp hybrid, it actually doesn't look too much different from just having 3 p orbitals, except we've mixed in that central s orbital in with one of the p's. So it changes its shape just a little bit. So let me actually go to my model here. Here's acetylene. Let me actually just show you the carbon. So there's a p orbital on that carbon, 1 above and 1 below. Here's another p orbital on that carbon. I've got that sort of in front of and behind. And then the sp hybrid orbitals will be going to the left and to the right. See? So now these sp hybrid orbitals will be able to overlap with other atoms to make sigma bonding. So let's add the whole molecule together. One of these sp hybrids will overlap with hydrogen to make the CH bond. The other sp hybrid will overlap with carbon to make the first part of the triple bond. But I need 2 more pairs of electrons to overlap. So the p orbitals that go above and below will overlap with each other. That'll make the second part of the triple bond. And then the p orbitals that are in front of and behind will overlap with each other to make the third part of the triple bond. So a triple bond consists of a sigma, which goes straight down the middle, a pi that goes above and below, and a pi that goes in front of and in back of. Right? So we always start with the sigma and then add on however many pi's that we need. So let's take a look a little more closely at how that structure works. I said they're 180 degrees apart since there's only 2 of those hybrid orbitals. The 2 unhybridized orbitals occupy the other axes. So right here, we see these sp hybrid orbitals making a sigma bond between the 2 carbons. That's in the middle. And then we've got 2 pi bonds. Right? There's 1 pi bond that goes above and below. There's another pi bond that goes to the left and to the right. So that actually explains acetylene structure. It is a 180 degree bond angle, which we could predict just from the little structure here, because that triple bond is 1 electron group. The CH single bond is 1 electron group, right? But remember what's always happened. We've had a sigma bond in between to begin with, 1 pi bond that goes above and below, and then another pi bond that goes in front of and behind in order for the triple bonding to work. let's review the main bonding patterns of carbon. These bonding patterns here will be the ones that we'll primarily deal with in this course. There actually is one more where carbon can make 2 double bonds, but we won't deal with that too much this semester, and when we do, we'll make a special case out of it. But these are the most common bonding patterns that carbon makes. So let's start with 4 single bonds like we saw with methane and with ethane. So just the regular single bonding carbons with patterns with carbon. To have 4 single bonds, I'm going to need to make 4 equal hybrid orbitals. So the one s will have to hybridize with the other 3 of the p orbitals. So hybridization is sp3. And that'll be all sigma bonds. Right? The carbon will be bonding to something like hydrogen out of all 4 tetrahedral directions. So 4 sigma bonds, no pi bonds. Right? And the bond angle will just be the tetrahedral bond angle, 109.5 degrees. So adding in a double bond will mean we have 2 single and 1 double bond. So I only have 3 atoms that I'm attaching to that carbon, so I need 3 hybrid orbitals. So that's going to be sp2. There'll be 3 sigma bonds, 1 each in the single bonds. The double bond, remember, it contains 1 sigma bond and 1 pi bond. So that's what makes up the double bond, a sigma and a pi. So bond angle is 120 degrees because the 3 sigma bonds will be evenly spread around that flat plane. So finally, 1 single bond and 1 triple bond will be sp hybridized, just 2 hybrid orbitals. So 2 sigma bonds. The sigma bonds are the ones that are occupying the hybrid orbitals in each case. To make a triple bond, one of those sigma bonds will have to be combined with 2 pi bonds. So just 2 of those hybrid orbitals means we have 180 degrees apart from each other. So I invite you to practice up on these bonding patterns. Don't just go memorizing this table here. That's not going to be helpful to you when you're identifying the types of atoms. Go back to these models that I've shown you on here and see if you can identify how that bonding works. When I show the hybrid orbitals on this one, we can tell that there are 3 hybrid orbitals on each carbon, and then there's 1 unhybridized p orbital. So this has to be sp2 hybridizing. So the third of the p orbitals is unhybridized. With acetylene, we show those hybrid orbitals. There's only 2 hybrid orbitals on carbon. Those make up the sigma bonds, and then there are 2 sets of unhybridized p orbitals that make up the 2 pi bonds. So I would really recommend that you explore these models, make sure you can understand why it is that those hybridizations are the way that they are.